PowerPoint. So our next guest is Dr. Jeff Lewis, professor at VIU, and I'm going to start calling him Dr. Climate Change. So he's going to do a presentation for us tonight on climate change, and without further ado, Dr. Jeff Lewis. Thank you.
Thank you very much to Elizabeth May for enlightening us all about the policy process that goes on. Because it is so important to understand what is happening worldwide and how we are trying to achieve the goals that have been set. Now, I've been asked today to talk about climate change and the climate change that's happening right now. And I'm sure that many of you have already heard a lot of what I'm going to say. So I'm also going to, change it up a little bit in hopefully giving you some information when you're having conversations with other people that perhaps don't share your perspective or are unsure of the science. Some things that you can use to help perhaps convince them, again, to help support appropriate actions and policies to avoid more extreme climate change. So I'll start off by talking about the overwhelming burden of evidence that climate change is happening and that we are the main cause of present-day climate change. It is essentially indisputable, and anyone that comes up with other alternatives either doesn't know what they're talking about or is intentionally trying to mislead you. To do that, I'll also go over the main causes of climate change. And I mean main causes of climate change throughout Earth's history. So there's sort of 5 main causes of climate change, and I'll briefly touch on each of them so that hopefully you'll be convinced, as I am, that humans are the cause of present-day climate change. And then I'll go over some of the main examples. And I could go on literally for hours about the science of climate change, but I'll try to keep it to about half an hour. And then at the very end, talk about how to avoid more extreme climate change, which Elizabeth May has already talked about, going over that 1.5 or 2 degrees Celsius threshold. So, again, Elizabeth has talked about the conference of parties. The science that we sort of use as the overall comprehensive reports that come out every about 5 to 7 years are written by a group of scientists called the IPCC, or the Intergovernmental Panel on Climate Change, which is a mouthful. But they are the group of scientists that were awarded the Nobel Peace Prize in 2007 for their work on climate change. And again, they don't do the peer-reviewed research themselves. They go and every 5 to 7 years review all the latest up-to-date research and write a really large synthesis report. It happens to be thousands of pages long. There's a number of different working groups, and the media usually picks up on one statement from all of that. And the one that came out most recently, the 5th assessment report, the statement was that it's extremely likely, and by that statement the scientists meant with greater than 95% certainty, that human influence has been the dominant cause of observed warming since the mid-20th century. And for a bunch of scientists to get together and actually come to an agreement on a statement like that is very powerful. Because by their very nature, scientists are very skeptical. And I don't mean skeptical in sort of a climate skeptic sense, which I think is a misuse of the term, but skeptical in that they question everything. And they will only come to an agreement if they are absolutely convinced that that is true. The other thing that's important to note here is it's not just this group of scientists that support this, but it's almost every national science academy from the leading countries around the world, regardless of what their administrations view. So Canada, US, China, Russia, Japan, it doesn't matter, but all of these national science academies, so other groups of scientists in these countries, support this statement. And essentially the science is settled enough for us to take very prompt action, as Elizabeth May has already mentioned. And a lot of people like to say, well, this is all an environmental movement, this is a bunch of scientists, we can disregard what they have to say. But often if you're trying to talk to a different group, it is important to talk about other people that also agree that climate change is happening, and that is a major issue right now. And the US military does not happen to be a bunch of scientists, and neither are they sort of left-wing hippies. And they state that climate change is a security threat, and that the impacts will exacerbate already pre-existing issues of conflict around the world. And they've just recently released a statement that said the Department of Defense sees climate change as a present security risk, not just a long-term risk. And so if the US military is also regarding climate change as a serious threat right now, it is not just scientists or people progressive agenda, it is essentially anyone that's had to deal with climate change. It's not just the military, it would be insurance companies, the World Bank, lots of different organizations. Anyone that's had to deal with the consequences of climate change have accepted that it's happening for a long time now. Oops, sorry. So, to try to concisely sum up what the roughly 3,000 to 4,000 pages of the last assessment report said, this is the main summary from that document. Humans have caused the majority of present-day climate change. The warming, unfortunately, is largely irreversible. Most of the heat is going into the oceans, and we tend to focus on the atmospheric temperature record, and I'll get to that in a little bit. Another one that's often not talked about is that ocean acidification rates are unprecedented. We are acidifying the ocean at a magnitude that hasn't been seen in millions of years. And that alone is enough reason to stop putting carbon dioxide into the atmosphere. And I will talk much more about that in a bit. To stay below 2 degrees Celsius of warming, most fossil fuels must stay buried in the ground, let alone trying to avoid 1.5 degrees. And again, I will talk about that. One thing to mention with 2 degrees Celsius is that it's not a hard threshold. It's that over the last 400,000 years, the temperature has been a bit warmer. It's been up to a couple of degrees warmer than pre-industrial. So we have something to refer back to understand how the climate might behave. But as soon as we start to get outside of that boundary, we start to get into an area where scientists really don't know what some of the consequences are going to be. And we start talking about climate destabilization. There are long-term effects, like the melting of the Greenland ice sheet, that once it starts to go, we may never be able to get it back. And we don't know where those thresholds exist, but we certainly know that the warmer it gets, the more severe and the higher the chance of those happening become. And so we want to try to stay well below 2 degrees Celsius, preferably below 1.5. We'll see. So to understand the science of climate change, we have to sort of understand what causes the climate change in general. It's a very simple equation. In equals out. So if the amount of energy coming into the sun is equal to the amount of energy that's leaving Earth, so we've got solar radiation coming in, shortwave radiation, we've got sort of heat or thermal energy leaving the Earth. If the two are in balance, then the Earth's climate is relatively stable. But obviously, if we change that balance in any way, if the energy from the sun gets stronger, we'll heat up. If it gets weaker, we'll cool down. Or if there's more thermal energy escaping, we'll cool down. Or if, like right now, there is less thermal energy escaping, then the Earth will heat up. When it is in balance, we say that it is in radiative equilibrium. That's sort of the fancy term for imbalance. And anything that causes the Earth's climate to be outside of that equilibrium, we call it a forcing. It forces the climate to change, or radiative forcing. And the 5 main things that cause climate to change throughout Earth's history are changes in how much energy comes from the sun. Obviously, the sun is a very important component into Earth's climate. We have changes in Earth's orbit, so how the Earth goes around and tilts toward or away from the sun. Changes in how much energy is absorbed at the surface, changes in how our atmosphere and our oceans circulate, and then also changes in our atmospheric composition. The important thing to note here, especially if you're talking to other people that might be a little bit skeptical, is that all of these are acting all the time. But at any given time, one or more of them might be stronger than another. So changes in solar output, the average energy from the sun hasn't changed in the last 50 or 60 years, so it can't be influencing Earth's temperature right now. Changes in Earth's orbit take way too long to happen. The shortest time is about 19,000 years, so it's insignificant for right now. Changes in the surface energy balance, or how much energy is absorbed, does play a role. We have land use change, deforestation, but it's minor compared to our change in our atmosphere. And then the changes in circulation, as we'll see, actually have a very strong influence on the year-to-year temperature, but not on the long term. So again, keep in mind that all of these are acting all the time, but at any one time, one can be more dominant than the other. So if we sort of sum up the main cause here, we can see here's average energy from the sun, and definitely from 1900 to about 1950 or so, there was an average increase in energy from the sun, and we do see that there was an increase in temperature that roughly corresponds. But since about 1950 or so, the average energy from the sun has been relatively constant, even slightly declining. And yet, Earth's temperature has been going up and up. And this is really what we're talking about when we talk about present-day climate change. We're talking about the increasing temperature specifically over the last 50 or 60 years. And the only thing that I've just discussed with those 5 main causes of climate change, the only thing that can explain that is the substantial increase in greenhouse gases. Not just carbon dioxide, but greenhouse gases in general. And the way that a greenhouse gas works is that it allows energy from the sun to come in. It's basically transparent to sunlight, but it traps the outgoing thermal energy or heat energy from the Earth and causes it to be warmer. And the greenhouse effect is a natural effect. So the reason why Earth is so habitable right now is that we have a greenhouse effect. Without it, the Earth would be about 33 degrees colder. It would be minus 18 degrees Celsius. So the greenhouse effect itself is natural and a positive thing for us, but we're concerned about amplifying it. It's like putting the greenhouse effect on steroids. And if we look what we're doing, enhancing the greenhouse effect, we can see here's the level of 3 of the most dominant greenhouse gases, carbon dioxide, methane, and nitrous oxide. Just to note that the scales don't go to 0, so it's a little bit over-exaggerated how many times it's increased, but CO2 has increased by about 40%, and methane and nitrous oxide have also increased substantially. But all of this spike in greenhouse gases is from us. So it's from burning fossil fuels predominantly. And this is the main cause of present-day climate change. The other way that we can try to understand, I guess, what causes climate change is to put what we know about the natural forcing. So volcanic emissions tend to put a lot of soot into the atmosphere and block sunlight. You'll see these really cold spikes in here, so that's typically a volcanic eruption. So we've got Mount Pinatubo, El Chichon. So if we look at the black line, that's the temperature change that we've seen since about 1900 or so. So that's actual observations. And then we run computer models and we have a look at what the climate should have been like if we just used natural forcing, so just changes in solar output and volcanic eruptions. And we can see that overall it does reasonably well until about the middle of the 1900s, and then it should have been relatively level or constant. And we know that because the average energy from the sun was relatively level or constant over that time too. And it's only if we include the anthropogenic component, or the component from humans, mainly burning fossil fuels, that we can actually explain the warming that we've seen over the last 50 or 60 years. There is no other explanation, unfortunately. So if we look at some of the impacts that we've seen, this is obviously a map of the world, but this is from February of this last year. And it was the hottest February on record. And it was not only the hottest February on record, but it absolutely shattered the previous record. And as Elizabeth May was talking about, the positive feedback or self-reinforcing cycle of snow and ice albedo, the reflectivity, we see there is much, much warming in the northern hemisphere and especially up around the Arctic, because all that snow and ice is melting back. Is revealing a darker land surface or ocean surface, which is absorbing more sunlight and further amplifying the temperature. And the Arctic is warming at 2 to 3 times the global average rate. So this is just February, and one thing about being a climate scientist is we want to be very careful not to look at any one month or 1 year. We want to look at long-term averages, and typically for climate scientists we look at 30-year averages, and maybe the shortest would be a 10-year average. So this was February 2016. Actually, July was the hottest month ever on record. It shattered all records as well. But we want to look at the averages. So here is the 2000s. Here's the 2000s, so 2000 2009, compared to a long-term average, a 30-year average from 1950 to 1980. So this isn't climate change that's going to happen. This is what has already happened. In fact, it's actually getting a bit old now. It's dated. But we can see that, just as we saw in that last picture of February, we see that the warming is greater over land, because land tends to heat up faster than the oceans, and it's much greater over the northern hemisphere and the Arctic because of that very strong feedback of snow and ice melting back. And we can see the temperature change here is already up to about 2 degrees regionally. And global average is about, what's being represented here, is about 0.5 degrees Celsius. So a very important point is that we might talk about a global average increase of 1.5 degrees Celsius or Celsius. But that doesn't mean that every location on the planet will be warmed by 1.5 or 2 degrees Celsius. We're already seeing a 2 degrees Celsius rise in temperature with a 1/2 degree change in global average temperature. So a global average temperature increase of about 2 degrees will lead to some regions being 8 degrees warmer, especially in the Arctic, and that will have major repercussions. One of the challenges of talking about climate and climate science is that there's often a lot of graphs. Graphs are great for scientists, but they're not the most effective way of communicating. As we've shown, I mean, scientists have known about climate change for a long time now, for decades, and we're still talking about it. We're still not taking enough action because scientists have notoriously been horrible at communicating the urgency required. So I do have some different visuals, hopefully that will help to work as well. But to put things in perspective, we're looking at sort of a pre-industrial average temperature, and this was that warming that we saw the last 50 or 60 years. Right now, last year, 2015, we already went over the 1 degree Celsius threshold, if you will. So we're already in 1 year. So again, we tend not to look at things by 1 year. We would actually take the average of the last 10 years, which means we're still a little bit below 1 degrees. But for a single year, we're already 1 degree warmer than pre-industrial. And the projection for 2016 is to be even warmer still. So we have a lot of work to do very quickly if we are to meet the 1.5 degree or even 2 degrees Celsius target. As I mentioned, we don't necessarily want to look at temperature by 1 year at a time. This is just a different way of viewing the same information, but we're looking at it by decade. So here is 1970s, 1980s, 1990s, the 2000s, and the 2010s will be warmer still. So even if we just look at the average temperature, the different colors, different lines, is that there's different groups that are working on the different data sets, and they might not agree on every year, but the overall trend is essentially identical. So we've got our measurements from the UK, not measurements, but groups that are showing all the data from the UK, from the US, all over. They might disagree again year to year, but overall it's the same. This is a wonderful graphic that I came across just recently, and we'll watch it just a few times. It's quick. But what it's doing is it's plotting every month, the temperature of every month since 1880. And it gets warmer as it goes towards the outside of the circle. So again, we'll let it start up again now that you understand what you're looking at. So there's 0 degrees, which is roughly our pre-industrial temperature. Starts at 1850. And we can see that not a whole lot changed. And then the first part of 1900, it started to warm a little bit. It steadied off in the middle of the 1900s. And then since about 1970, it has rapidly increased. And we are getting very close to that 1.5 degrees Celsius threshold. We'll watch it one more time. I'll stay quiet. So one of the challenges of communicating about climate science is how do you get the message across? And sometimes it is just trying to say the same thing in as many different ways as possible, using as many different graphics or images. So hopefully there's something in here that you might be able to use as well. We talk about the temperature record. This is showing not just the atmospheric temperature record, which is this thin brown line. So it's kind of showing the same thing that I was just showing, but it's putting it into perspective of the ocean as well. So here is the surface ocean water and deeper water, and it highlights that when we look at where is all the heat from global warming going, 90% of it is going into the ocean. So we are fixated on looking at the atmospheric temperature record because that's what sort of influences us the most, but that doesn't really tell the whole story. Most of the heat of climate change, of global warming, is going into the oceans. And so just because we've got a snowstorm that's really severe on the East Coast does not mean that climate change has stopped. We want to make sure we're looking at the whole data set as well. And what happens with that, this is where things get a little bit more challenging, is that I mentioned that one of the main causes of climate change was change in ocean circulation. And I'm going to see how far I can move. There we go. So we know, we've heard in the media now, we've got El Nino and La Nina. We've just been through a very strong El Nino. And very quickly what that is that normal conditions in the equatorial Pacific region here is that we've got winds blowing from east to west, and that tends to move all the warm surface water over to this side of the ocean, and it buries it down. It means it's not in contact with the atmosphere. And under an El Nino condition, what happens is that as the trade winds weaken, so the air flow weakens, all that warm water that was stored down deep out of contact with the atmosphere actually sloshes back across the whole surface, and this is what we're looking at. This is a temperature anomaly, so the temperature change outside of normal. And under an El Nino condition, all of that warm water is now available to interact with the atmosphere and really heat up the atmosphere. And so under El Nino years, because you've got this hot water bottle essentially underneath the atmosphere is much warmer, and we see that. So the graph up above here is showing all the years that are El Nino years in orange. So 1998 was a very strong El Nino year that was very warm. And then we also have conditions that are called La Nina years. So this is when the winds are blowing really strong and really bury the warm water, and it actually brings up a lot of cold water, and so it cools the atmosphere. And this cycle, going back and forth between El Nino and La Nina, it takes between 2 and 7 years. On average, it's about 5 years or so. So when we look at the temperature record and we see that it's going up and down, up and down, up and down. In fact, we had 1998 was very strong, and then the next couple of years, people said, well, it's not as warm, therefore global warming has stopped. And it goes back to my original point that there's 5 main things that cause climate change. Any given time period, one or more can be more dominant. And if we look at the year-to-year changes, this El Nino La Nina is actually one of the strongest influences on the year-to-year temperature change. So the orange bars are typically warmer than the blue bars here.
From the front, but there was also Pinatubo 99.
Absolutely. So there are other factors that come into it whenever we have major volcanic eruptions like Pinatubo or El Tichon. That can cause a cooling even though it was an El Nino event or a warm event. 2014 was actually very significant in that it was statistically tied as one of the warmest years on record, but it was significant because it was not an El Nino year. It was just sort of an average or normal year. And then we had 2015, which was a strong El Nino year and absolutely shattered all records. So again, 1998 it was warm because it was El Nino. 2015 was warmer than 2014 because it's El Nino, but the reason why 2015 is significantly warmer than 1998 is because of climate change, is because of greenhouse gases increasing this long-term trend in temperature. So after 2016, is it just going to continue to get warmer every year? Absolutely not. We will go back into El Nino or La Nina conditions. We'll have some cooler years, but if we look at that long-term trend, at least a 10-year trend, we see that it will continue to go up and up and up, unless we do something about it. Sea level rise. Sea level rise is another major impact, and one that's very significant for us because we live on the coast. We definitely have some low-lying regions on the coast. We have a lot of money invested in infrastructure, like our ferry terminals, that are highly dependent on sea level rise. The media obviously picks up on this, looking at Vancouver, Canada's east coast, most around the world. There was just an article in the CBC News about a community in PEI that will be essentially underwater in the next 50 years or so because sea level continues to increase. So what happens is that as the temperature warms up, there's 2 main factors. One is that land-based ice, whether it's the ice sheets of Greenland and Antarctica or glaciers in the mountains, they melt and that water flows into the oceans and the ocean continues to rise. The other one is that the ocean water just gets warmer. Remember that the oceans are absorbing 90% of the heat of climate change, and it's called thermal expansion. When water warms up, it expands. It can't really go sideways, so it goes up. And right now it's about a 50-50. 50% of sea level rise is from melting glaciers and 50% from thermal expansion. We've already had a 20-centimeter rise in sea level since pre-industrial, and the projections for, say, 2100 Right now, from the IPCC, it goes up to about 1.2 meters, but if you look at the full range of studies, it goes up to about 2 meters. So typically, sea level rise is, usually people that are betting on this are suggesting between half a meter sea level rise and 2 meters of sea level rise. Again, depending on what happens and what we do. One thing to note is that the rate of sea level rise currently is about twice as fast as the long-term average. We're seeing that sea level rise is accelerating because things are getting warmer. We have those self-reinforcing cycles of positive feedbacks that again are amplifying the warming where we have snow and ice. Ocean acidification. So even if we ignored everything we know about climate change, even if CO2 had nothing to do with changing temperature or climate, this reason alone is enough to stop putting carbon dioxide into the atmosphere. So a recent UN report stated the global economy could be losing as much as $1 trillion annually by the end of the century if countries do not take urgent steps to stop ocean acidification. And again, it is something that's not sexy. The media does not pick up on it all that much. But as scientists, this is probably one of the most pressing issues related to climate change. So it's not actually climate change, but they're both caused by the same thing. As we put more and more carbon dioxide up into the atmosphere, the oceans absorb more carbon dioxide. Colder water absorbs more carbon dioxide than warmer water, and therefore it gets more acidic. So CO2 and water combine to form a weak acid, carbonic acid, and a lot of the base of our food chain, our phytoplankton and our coral, have shells made of calcium carbonate that dissolve in acid. One of the labs I do in class is we drop some acid on calcium carbonate and watch it fizz and it gives off CO2. But what we're already seeing here is that shells are already dissolving under current levels of ocean acidification in some of the oceans, especially in the Southern Ocean here. It's a pH scale, I won't get into that at all, but we've already seen roughly a 30% increase in our surface ocean acidity since pre-industrial, and at the current rates of putting carbon dioxide into the atmosphere, we will be changing the acidity of the ocean to such an extent that we haven't seen in 300 million years. So by the year, well, 200 years from now, we won't have seen changes like that in 300 million years. So we're in a very short time period changing things on a geological timescale. By the year 2100, it would be an ocean acidity that we haven't seen in the last 50 million years. So we're talking about major geological changes. Again, this is reason alone to stop putting carbon dioxide into the atmosphere. And you'll often hear people start talking about other things like geoengineering. Let's try to cool the planet or do other things to prevent global warming. Make sure that it also addresses ocean acidification, which the only way to stop this, and we know what it is, it's very easy, we stop putting carbon dioxide into the atmosphere. Of course, what the media does pick up on is the extreme events. And this is the last sort of impact that I'll talk about. Extreme events are sexy, right? There's major damages, there's lots of media reports about them, unfortunately. So we see here we've got the 2015 drought in California. It's been actually a very long drought. But they can put actual costs to that. So about $2.7 billion for the 2015 drought. Texas 2011 drought cost about $7.6 billion. So if you put things in dollar terms, then people start to pay attention. One of the main things from a scientific perspective about extreme events is that often we've been asked, was this event caused by climate change? And for a long time we always had to say, well, no one event is caused by climate change, but if we look at the long-term trend, we would expect to see more of these events occurring. And then James Hansen flipped it all on its head back in 2012 and said, instead of saying, was this event caused by climate change, we should be asking, what was the chance that this event would occur without climate change? And I'm going to try to explain this graph, even though it's fairly busy. So what they did is they just looked at the average temperatures from 1950 to 1980 and said, around the world, about a third of the world is normal temperature, about a third of the world is considered hot, and about a third of the world is considered colder than normal. And these are all based on the local normal temperatures. And we can see that. So here is what they considered hot, so the top 33% of the area, and that was about a third. As we're going along here, that's what this dashed line is, a third. And then in about 1980s, we saw that what used to cover about a third of the Earth's area was considered hot, now covers more than 2/3, almost 80% of the area would have been considered hot. Now it's sort of a new normal. And where things get really interesting is when we start looking at events that had a smaller chance of happening. So very hot only covered about 2% of the Earth's surface. Now that is covering about a third of the Earth's surface. And then these extremely hot, so there was almost no chance of it happening. So less than 0.2%. So that's this flat line here. So it wasn't happening. And now that's covering about 10% of the area. And scientists are coming out and every year releasing reports, usually from a couple years previous, saying these are the extreme events, and yes, we can conclude that they were caused by climate change because the chance of them happening without climate change was next to zero. There was almost no chance of these events happening back in the 50s, 60s, 70s. So the main conclusion from James Hansen et al. Paper in 2012 is that extreme temperature events are 5 to 10 times more common. And depending on what events we're talking about, some of them are now 20 times more common. The heat waves, those ones are much easier to contribute to climate change. Things like flood events are more challenging because precipitation is far more variable. So, avoiding more extreme climate change. This is the, again, current temperature record from about 1850 to 2000, and then what the IPCC, or that group of scientists, they go and review all the literature that's been done for the climate modeling, and the models try to, again, put their best estimates of what we are going to do, as well as understand the internal variability within the climate system, and they try to project out what different scenarios there might be. So if we just focus on the line up to 2100, there's actually 4 colors. There's this blue one here, which is our best case scenario, and then there's a lighter blue one. And you can think of those as 2 sort of extremes of the same thing, where as a global community, we get together, we really move on the Paris Accord, we strive really hard to limit warming to 1.5 degrees, and this is our best case scenario for that, and this lighter blue line would be the worst case scenario if we really try super hard and work together as a global community. So you can see we're barely making it under the 2 degrees Celsius, and even if we try really hard and don't do as well, we are going to surpass that and be about average of 3 degrees. The other 2 lines here, this yellow or orange line and then the red line, is if we don't get together as a global community, we've got sort of 2 end members. This one here is just business as usual, and the yellow one or orange one is if we try individually as individual nations to try to do something about climate change, but we're not working together as a global community, this is probably what we'll end up with. And unfortunately, we're currently tracking along this pink line. So by the year 2100, this is putting us up, the solid lines are the average, and then you sort of see the sort of extremes of each one there. So this is on average putting us up to about 5 degrees Celsius by the year 2100. And the reason why the IPCC released this image that actually goes out to 2300 is to remind people that the world doesn't end in 2100, and that what we do now has ramifications even farther in the future. And again, so we can see this best case scenario is a couple things to note here. One is that we actually start to cool things back down and we stabilize below the 2 degrees Celsius threshold, around 1.5, which is fantastic. But even if we all try and don't do as well, we continue to have warming until 2300. And as we start to get warmer, as we start to get above this 2 degrees Celsius, we start to get into temperatures where we don't have analogies in the past. We can't really look back in the recent past and see how climate would behave. And so we can see that the range of uncertainty is much, much greater, because we really don't have a good idea how climate will behave when it starts to destabilize and go into temperatures where we really have not seen before, not in the last couple million years. So again, we want to aim for this. Elizabeth May has explained how we can attempt to do that as a global community. This is our vision. This is what we're trying to achieve. And right now we are going along this line here. Another very important figure that the IPCC released, and also probably one of their worst as far as communicating, is this one. And it's a very important message, and it is that the cumulative total human emissions of carbon dioxide, so that means what we have released since we started burning fossil fuels, is related to temperature. So as we start to burn more fossil fuels, the temperature increases. And forget all the colors and everything else. The main message is here, and I'm going to simplify it, is that it's a straight line. So we'll go back one. Basically all this color, everything else, doesn't really matter. It's basically a straight line, which means that as the total amount of emissions that we burn goes up, the temperature varies proportionally. And that's very important because we've already burned more than 500 gigatons of carbon, which is why we're sitting up here at about 1 degree Celsius, but it allows us to work back from any target that we set, and I'm just going to use the 2 degrees Celsius target because it's easier for me to talk about. So we've got the 2 degrees Celsius target. It allows us to go this line and look down and see what our total carbon budget is. So what we can burn. What's very important here is that it doesn't matter how long it takes us to burn this. We don't talk about carbon intensity. This is just the total amount. So if we only have, say, 300 gigatons of carbon left before we surpass this 2 degrees, we can burn that all tomorrow, or we can burn for the next 100 years. It doesn't matter. The temperature, once all of that carbon is in the atmosphere, will equilibrate at about 2 degrees Celsius. So if we do track that, here we go. If we do track that, this is about where we are now. So we've burned about 545 gigatons of carbon in 2014. And in order to avoid this 2 degrees Celsius threshold, we've got a window of about 800 to 1,000 gigatons of carbon. 1,000 is if we ignored all the other greenhouse gases, which we can't, so we should ignore that. And we should focus on the 800 because that's the amount of carbon that we can actually burn and still stay under 2 degrees Celsius. Obviously, if we're trying to stay under 1.5, then we'll have to burn less than that. These circles here, so this is what we have left to burn. We understand now we have a budget. We can burn about 270 gigatons of carbon and hope to stay under 2 degrees Celsius. Unfortunately, our current proven reserves are about 780 gigatons. And a proven reserve is something that we know is there, it is economically viable now with existing technology. So this is what we have already explored for and found and want to use up, at least companies want to extract that. And then if we look at potential reserves, so if we look at the amount of oil, natural gas, and coal that we have left, it's about 1,500 gigatons of carbon. So unfortunately, we cannot just wait until fossil fuels run out. We have to leave not only the reserves that we aren't aware of, but we have to leave a whole lot of the carbon, of the coal and oil and natural gas in the ground that we already have explored for, have poured a bunch of money into in researching for, and we know is extractable. We have to leave, depending on whose numbers you believe, between 65% and 80% of known fossil fuels in the ground. Which leads us to what's called unburnable fossil fuels. So these are the fossil fuels, again, that we know is in the ground, but we know we can't burn if we want to stay below 2 degrees Celsius. And different groups are now going around and they are not only looking at where the oil, coal, natural gas should stay in the ground, but which ones have the most impact. There's a much more detailed study to go by different countries and look at exactly what proportion of each of these fossil fuels should stay in the ground. But basically, most of the coal needs to stay in the ground. About half of our natural gas has to stay in the ground, and about a third of the oil, because we're already running out of oil. And even Mark Carney, who was a former governor of the Bank of Canada, current governor of Bank of England, has stated that climate change threatens the financial system. Oil can become a stranded asset. So not only does it make sense to not put carbon dioxide into the atmosphere from an environmental or social perspective, but even now from a economic risk assessment, it does not make sense to be investing in oil and gas exploration and even extraction of a lot of these if we're serious about avoiding that 2 degrees Celsius. Justin Trudeau has stated that we will have a price on carbon by the end of the year. As soon as we start to ramp up the cost of carbon, a lot of the investments that are being made, they can't have returns. So it makes financial sense not to continue to invest in oil and gas. And I'm going to end there. To sum it up, essentially humans have caused the majority of present-day climate change. To prevent more extreme climate change and to stay below 2 degrees Celsius, preferably 1.5 degrees Celsius, most fossil fuels must stay buried in the ground. And the only way that we can do this is not just through individual actions, which are fantastic, but through collective action to support more appropriate, again, actions and policies that will help us to avoid more extreme climate change. Thank you very much.
So I want to thank Jeff for that very informative presentation. I've got some questions of my own that I'll be able to share with you from some online folks that will be provocative, I believe. But I think that if there's any doubt, I think most of us are here because I think we understand and accept the realities of climate change and the impacts that it will have on all of our lives, and that it is already having on our lives, not only in terms of our daily lives, but also into the greater health of our environment, our planet, our food systems, our energy systems. The only thing that I see is an economic argument against climate change. The only people who argue with me about climate change are people who believe in oil extraction and say the economy will be hurt by limiting oil extraction and the burning of natural gas or the use of fossil fuels. They also tell me that they need fossil fuels for things like my electric car, which are all very true. What we're talking about is the way that we use the remaining fossil fuels that we have available to use within that budget, if you will, to make a transition. Not a transition fuel of LNG, like is talked a lot about our provincial government, but about a transition to a new fuel. Cleaner burning fuels are not the answer. Solar, proper hydroelectric, small pump storage systems, wind are all power systems that are not only environmentally sound but are economically viable. So one thing that I can share with you is my hobby of climate change centers around the economics and the boom that can come from making the transition to clean energy. You won't have to send people through carbon-intensive flights to the northern Alberta to work in the oil fields anymore. They can work in their local solar and wind power plant. You can use local water reservoirs to do pump storage to act as a battery in an environmental way of using hydroelectric power without having to make giant Site C dams that flood farmlands and endanger and violate the rights of our Indigenous peoples. So if there's a message that you can take out from this is the transition can be economic boom, and it can be a lifestyle boom that shows that we can preserve our environment, produce clean energy, and produce jobs that stay in local communities through smaller distributed power. I could sit here and talk to you for hours about how that combats terrorism, provides electricity security, provides against other natural disasters, and makes our communities more resilient and secure. But that's not what tonight's about, and we need to get to the questions. So when you leave this, take this information, and for those people out there that try and make an economic argument against the transition away from fossil fuels, talk to them about the economic boom that can come from that transition and how that can play a part in a new economy and a new energy economy for all of us. And if you notice in the fine lines of some of those big oil companies out there, they're shifting their own investments into clean power resources. So they know, they've heard the Mark Carneys of the world telling them that they're at risk, but it doesn't mean that they're not trying to make the last gasp for every dollar they can. Unfortunately, it'll come at the expense of all of our communities and our livelihoods for not only us, but our children, our grandchildren, and so on and so on. So I want to thank you all very much. I'm going to turn the microphone over to David. I just want to have one more round of applause for Dr. Jeff Lewis and Elizabeth May. And I hope that all of you will join all of us in being the evangelists, if you will, I get to stand in a pulpit and say evangelist, that's a good thing. But the evangelist for a clean energy economy, for clean energy lifestyles, doing the things we can at home, but also, as Jeff just said, we need to push our representation, whether it's in politics, our elected officials. I know Kate's here from North Cowichan, who's also a big ally in that effort. But we all need to raise our voices, and when we get those opportunities to talk to other policymakers in the federal and provincial governments, when we go to the ballot box to vote, we really